Okay. Yes, so I'd like to thank the organizers, Kim and Ms. Alain, for bringing us here. I mean, you did all the work, I did nothing. This is an introductory talk. Sure, we talk about forms and their uses. And so the point of this talk is that people, I mean, since the discovery of quantum invariance of links, people studied webs, which describe representation, intertwiners for representations of quantum SL3 and quantum SLN, starting with the work of Greg Kuperberg. And so these webs, they describe intertwiners between representations of quantum group. And this representation video is a special case of the Reshetikhin-Turaev invariance of links. But so these webs, they have additional integrality and positivity properties. Specifically in the case of SLN, and you also see exterior powers. So you see in this theory of webs, you see fundamental representation V of SLN, and you see its exterior powers, but in the quantum sense, so quantum exterior powers of V and intertwiners between that and the products. And in this particular case, this case also corresponds to minuscule representations of simple V algebras and quantum groups. In this particular case, you get these additional properties. And then these properties help a lot with clarification. So when you look at clarification of quantum invariance, clarification of Reshetikhin-Turaev invariance, then it's the best known examples of these clarifications. They're specifically for colorings of link components by minuscule representations of GLN. So in this case, the link homology has several equivalent definitions, and it has the best known functoriality properties. So it's a special case. And at least at the current level of understanding, this property of intermediate calculus, of web calculus, helps a lot. So let me I'll mostly look at the SL3 case. And SL3 webs after Kuperberg. So let me just recall them. So we look at planar trivalent graphs. Every vertex is trivalent, and it's either an in vertex or an out vertex. And this corresponds to basic intertwiners, an element of in the space of invariance in the third tensor power of a fundamental representation. You take V cube, take invariance for the quantum SL3. This is one-dimensional, and this diagram represents a vector there of the dual vector, depending on orientations. And you can build general planar networks out of this elementary vertices. And then this network gamma, so you build a closed trivalent graph. Let me give you a particular example, but in general, it's more chaotic with no symmetries. But if you glue a network in a plane out of these vertices, and you get a graph of this form, gamma, and the Kuperberg invariant, P of gamma, it lies in Z plus QQ inverse, has no negative integer coefficients, and can be defined inductively, saying the invariant of the closed circle is quantum free, which is q squared plus 1 plus q minus 2. If you have a region which has two sides, a diagonal region, then this graph can be simplified by saying it's invariant as quantum 2 times the invariant of a simpler graph, where quantum 2 is q plus q inverse. And if you have a square facet, then its invariant can be simplified to the sum of the invariants of these two graphs with fewer vertices than the original graph. And you can check that these invariants, these relations are enough to simplify any planar graph of this form. Because you always have a region with no 2 or 4 vertices, the graph is bipartite, because every vertex is an out vertex or an in vertex that give you bipartite decomposition. So, and you can check that this is well defined, and you get the property that the invariant P gamma of any such web, closed SL3 web, so you can close, so no boundary, closed SL3 web, is in Z plus QQ inverse. And from these closed webs, you can pass to invariants of links using the skein rules. So for link L, it's invariant P of L. It still has integral coefficients, but they're not positive in general, so it's in Z QQ inverse. And that's sort of the expectation at the time. So there's a codification of the story that goes back slightly over 20 years ago. And so what was the motivation for this codification? At the time, we knew a codification of the quantum SL2 invariant of links of the Jones polynomial. So Jones polynomial can be lifted to a homology theory, which is bigraded, and its only characteristic recovers the Jones polynomial. So how to do something similar for SL3 links, SL3 link invariant, and SL3 webs. So if we would want to kind of upgrade SL3 invariant of link L, realize it as the only characteristic, some minus 1 to the I, u to the j, rank of some homology theory, hij of L, some over I and j, where we want to link, we want to assign bigraded homology groups, hij of L, with this order characteristic. We want some kind of functoriality. So we want a cobordism between links to induce a map of homology groups. So one speculation was that codification of link invariant should also include codification of P of gamma for webs gamma and more general diagrams that you can build as combinations of these two diagrams and these two diagrams. And you expect that these skein relations, they are 3-term relations that can be that are replaced by long exact sequences of homology groups of these three diagrams. And you also expect that to a web gamma, you want to assign homology groups, but you expect that this assignment is simpler than the assignment of homology groups for links, because the invariant for planar webs has positivity property. It takes values in Z plus QQ inverse. So you expect that the invariant has codification, which is only singly graded. So you want H of gamma to be just the sum H j gamma, j in Z, such that graded dimension of H of gamma, so sum rank of H j gamma q to the j, that this is the invariant of the web gamma. So the idea was to try to kind of break down the complexity of this construction and first build homology only for planar webs gamma. And for them, we don't actually need homology groups. We need a graded vector space. So it should be simpler than homology. And then assemble these groups together by induction on the number of crossings of a diagram. So if you already have homology group for this diagram, and a map between them, then we can pass to homology group of the diagram with one more crossing and then iterate this construction. So the idea was to simplify things in this way. And so now things are reduced to working with with webs, planar webs. So how to build this homology theory? So if you look at this scale relation, so the homology, the quantum invariant of a circle should be this cube squared plus 1 plus q minus 2. But you also want functoriality. So to a gamma, you assign homology of gamma. So this should be graded vector spaces. But now you can look at interactions between these webs. And interactions between webs, some kind of cobordisms between webs, should be assigned maps between these groups, because you want something functorial. So the idea is to look for a sort of TQFT-like functor H to a web gamma assigns homology groups H of gamma, and to a cobordism between gammas assigned maps of homology groups. So what would be a cobordism between gammas? Well, for instance, we want to have a map between homology of this graph of this web and homology of this web, so that when we take the cone of this map, we recover homology of this link. So how can we come up with a cobordism between these two webs? So let me draw one of these webs here, and the other web is shown here, the bottom. So there's actually a canonical cobordism between these two, which I call a singular saddle. So in this cobordism, you start with two parallel lines here with, let me call this web gamma null, and you merge them close to each other until they kind of share an interval which then expands. And you see that this cobordism is going to be similar. So we'll have a seam here, which such that its neighborhood consists of 3 plates. So 3 have planes. So we want singularities of our webs to be of this type. And then to this cobordism from gamma null to gamma 1, let me call this cobordism F. We want to assign a map H from H gamma null to H gamma 1, H of F. And then we hopefully can use this map as a step in the to build homology of the diagram with a crossing. So we want now why a TQFT functor? Because the invariant P gamma has the property that P gamma 1 union gamma 2 is P gamma 1, P gamma 2. And you expect that this multiplicativity is lifted to the multiplicativity for the homology groups H gamma 1, gamma 2 should be isomorphic to H gamma 1, tensor H gamma 2, which is a TQFT property. So we're looking for a functor that to a planar web assigns homology groups, well, graded vector space, and to a cobordism, it assigns a map between these vector spaces. And this functor is monoidal. Yes. This. Yeah. So we sort of so we're trying to first do something in the situation. First, we're trying to categorify a positive setup, integral positive setup, because that should be easier. And then once we have that, we want to pass to the next level. We want to categorify when we don't have positivity, which would be clarifying invariance of diagrams with crossings also, not just planar webs. So planar webs, they have especially simple invariant in the sense that it has non-negative energy coefficients. But if you take links, or if you take more general diagrams built out of both crossings and, I could take this diagram and add a crossing to it. So you can look at this more general diagram. So we want to build things in steps. So first build something for planar webs without crossings, because we have positivity of the invariant in this case. and then extend to more general diagrams, including diagrams of links. But so the motivation, we sort of want to have maps assigned to the singular cobordisms between webs, which we call forms. Which would also, if you have such maps, we'll be able to extend to homology of links in this way. So how does this work? So let us look at the simplest examples. If you take our graph to be a circle, then its quantum invariant is quantum free. So what should h of gamma be? So there should be functoriality. So if you have a cobordism, so we have a cobordism between unions of circles in the plane. For instance, we have the merge and split cobordism. We have the cobordism from nothing into circle and back. So this tells us that h of gamma should be a commutative Frobenius algebra. Just because it's essentially it's a 2D, it should be 2D TQFT, but restricted, but where things happen for surfaces inside R3, but that's a minor technical detail. So we want our homology groups to be, for the circle, to be a commutative Frobenius algebra. And there are not that many choices if the algebra has this graded dimension. So to name let me just first do it let me shift the degree so it's 1 plus q squared plus q to the 4th. Then, of course, this is the graded rank, excuse me, of homology of CP2. Okay. So let me call this algebra A. This algebra A can be written as, can be written as Z of x modulo x cubed, where x is in H2, CP2. And this is indeed a commutative Frobenius algebra with the trace epsilon. So here you can choose some invertible number. I mean, somehow I ended up choosing a long time ago -1. So let me just look at the trace map from A to Z, which is just integration over the top degree cycle. So again, why we forced into this? Because we want forms, cobordisms between graphs, to induce maps between the corresponding groups, and then which tells us that in this case we should have a Frobenius algebra as our state space, as our homology group, and there are very few choices here. Essentially, just one choice. Then this map corresponds to a unit element from Z to A. This is multiplication from A squared to A. Now there's a minor discrepancy because here it's balanced Q polynomial, but here it's unbalanced. It's in degrees 0, 2, and 4, the degrees of homology of CP2. This is minor. We can take this homology of CP2 and shift the degree down by the overall grading down by 2, so that it's balanced between degrees -2 and 2. If you do this, then given the cobordism, the surface S between unions of the circles, then the degree of the induced map H of S, this is map H of S, this is map H of S, is going to be -2 for the characteristic of S. So the degree is not, I mean, the map doesn't preserve the degree, but it's shifted by a number which depends on the characteristic of the surface, which is okay. Now, more generally, if you have, suppose that you have more general web gamma, which has a symmetry axis. So here, this web gamma This is sort of the next step in complexity. This is a circle, has no vertices. This gamma has 2 vertices. But this gamma has a symmetry axis. So you can glue it out of 2 pieces by flipping this to the other side and reversing orientation. And in this situation, all this h of gamma is an algebra. I mean, assuming functoriality, h of gamma is an algebra because you can take 2 copies of gamma. And so you have the symmetry axis. You can create a cobordism which rotates this half of gamma to the other half of the other gamma in this way, and this identity here. So you can have a cobordism into just one gamma. This diagram, so you kind of couple this half to the other half of the second gamma while doing nothing on the other 2, and you get a cobordism from gamma union gamma into gamma. And when you take homology or state space of this graphs, you get a map. It'll tell you that h of gamma has multiplication, which is associative, and you also have the unit element obtained by looking at the cobordism from nothing, from the empty diagram, into gamma, where you sort of rotate one half to the other half in this way. And this map from the ground ring to h of gamma behaves like the unit element, because if you compose this map with the multiplication, you get the identity map on the other copy of gamma. And this tells you that h of gamma is it's associative algebra, associative unital algebra. And this is just a very general remark. Whenever you have a TQFT, so whenever you have a TQFT, you can do this if your n-1 manifold has a symmetry axis. Okay. So this is completely general. Whenever you have a TQFT in dimension n, if you have an n-1 manifold with a symmetry axis, then its state space is going to be an associative algebra, unital, and you also have trace. It's also Frobenius, because just flip this cobordism the other direction to get the trace map from the cobordism from gamma to nothing, and on the level of state spaces, you get a map from here to the ground ring, giving you Frobenius algebra structure. So, questions? Yeah. So on one hand, we have all we did, we took a web which has a symmetry axis, and then necessarily h of gamma isomorphic to h of gamma tensor h of gamma. It has multiplication. Now, if you were to compose this cobordism, the unit cobordism, with this cobordism, that's identity. So that's just saying that this element is the unit for multiplication. And this is completely general. You can use any TQFT in dimension n, and then as an n-1 manifold, to choose any manifold with an axis of symmetry.
So what I'm asking about is all this line segment that goes through.
Yeah, so for this cobordism, you can start with one half and then rotate it like it spins. You can multiply it by an interval and then just kind of rotate it like a fan. Rotate it like a fan until it goes to the other side. So just rotate it half of gamma. And this is completely general principle then for n-1 manifold with a symmetry axis in a TQFT. Always its state space is a unital associative Frobenius algebra. So for us, let us think what it means for the state space of this graph gamma. So we want, that means that h of gamma, let me call it B. So it should have all these properties. all these properties. Plus, notice also that there are cobordisms where we start with this graph gamma, and we put a little circle somewhere near one of the edges. Then there's a cobordism where the circle is merges into that corresponding edge. And this tells us that for every edge, we should have a map from homology of gamma, B, tensor, homology of the circle A into B. And so we're looking for, we're kind of trying to guess what the sphere should assign to the simplest graph with 2 vertices and 3 edges. Should assign some commutative, should assign a Frobenius algebra. And this Frobenius algebra should have an action of A. A is the homology of CP2. And this action should be for every edge. For every edge, you can put a circle near an edge and merge it with gamma. So there should be many commuting actions of A on B. And graded rank of B is given by, well, according to these rules, right, if you take this graph, it's quantum invariant is quantum 2 times quantum 3. Apply this relation once to reduce it to a circle, and then circles 1, 3. So it's this. But notice that we had a shift here when we matched it to the homology of CP2. So I'll just say up to a shift is going to be 1 plus q squared, 1 plus q squared plus q to the 4th. And we already recognize this as coming from CP2. So this should come from CP1. And there are not many choices. So we should take as B the homology of full flags, FL3 of flags, which consists of all flags of subspaces L1 and L2 and C3, one-dimensional, two-dimensional. And from these flags, there are many maps into CP2, because you can forget L1, or you can forget L2, some variations of these maps. So there will be several maps into CP2, and maps back from homology of CP2 into homology of FL3, corresponding to these cobordisms. To this cobordism. So this turns out to be the right answer. So we can just take this homology of flags as the state space of this graph. Yeah, so things are oriented, and we want to keep track of orientations. We want to keep track of orientations of our webs, and our forms also carry orientations which are compatible with orientations of their boundaries. So everything is oriented in a compatible way. Okay, and then so it turns out that if you use this data homology of FL3 and homology of CP2, then this is enough to build this TQFT for cobordisms between webs. I also want to mention that it's convenient to add additional decoration to the story and represent a generator X of the homology of CP2 by a dot on a facet of the form. So this X and disk with 2 dots will be X squared. So at 3 dots is X cubed, which is 0. Because then when you're working with this graph, with this unit form, unit cobordism into this graph, then you can add dots on various facets to get we got monomial elements of this ring. Yeah. So in this example, there are no dots, so it corresponds to the unit element of the homology, but dots, so dots sort of represents this generator of the second homology of CP2 locally. But so this would correspond, for instance, to maybe x1, x2. There are two dots on the second facet, so it's x1, x2 squared. And then if you apply the trace map, the trace map, you'll be taking the trace x1, x2 squared. So then you can look at the rules for the homology of CP of flags in this basis. So there is then this is a possible basis of the homology. We'll just take the top degree element. This does not to be enough to build this. Yes. Oh, you cannot hear. I can just try to speak louder.
No. It has to be recorded. Just take a picture.
Okay, so I just have to. So just off the record. Off the record. Questions? Okay. So.
What about partial flags?
So in this example, it's the C3. So partial flags, they just CP2 that responds to a circle.
Like
Yes. Partial flags, I mean, you have a circle, so you don't see partial flags on this example. But you still need some kind of state space for more general verbs. And this approach is not enough, so you need to do a little bit more. Say that what you want to do is for something with more general verbs, and then you want to say elements in state space of gamma is represented by forms F. Form F and the boundary of F is gamma. So you want to represent elements of a string. Yes. Yeah, so you want to represent elements of a state space. Can you hear it? You can represent elements of a state space by forms F with boundary gamma. And again, there could be dots. And then you just kind of use a trick, and you say that H of gamma has a spanning set. I'll just say symbol of form F such that the boundary of F is gamma, and there's a relation sum of AI Fi is 0 if for any closure, if for any way to close gamma on the other side using some form F prime, if for any F prime, a form from gamma to nothing, if the sum of AI times some kind of evaluation F prime Fi is 0, where what is evaluation of F prime Fi? So take F with boundary gamma, F prime on the other side, glue them together to get a closed form. And now this closed form, let me do an example where this was our form F, some dots, and this form F prime is similar. F prime. Then as you glue them together into F prime F, so you see the seams, you see the singular circles of the closed form. And the idea is to use the Frobenius algebra structure of A, homology of CP2, and B, to compute the value of this form. How? For instance, we can do In this example, you can just pull all the single circles away from each other. So in this example, there are two circles. So do surgery on this tube. There is a tube here. If you take a cross-section of this tube, you see a circle. Circle has a state space given by A. A is a Frobenius algebra, so you can take the circle, draw it this way, and kind of cut it in the middle using Frobenius algebra structure, where this would be a sum over basis elements xi of your A, and here are the dual basis elements yi. In this case, there are 3 basis elements. It has dimension 3. So you can do surgeries to split this circled seams away from each other. And when you do this, then after you do this, then every seam, you'll just have 3 disks from its 3 sides, possibly with some number of dots on them. But this form evaluates to the trace of a monomial in X's, because if you add the cap at the top and you just have 3 disks, you have 3 disks, possibly with some number of dots on every disk. So you're evaluating the trace of the corresponding monomial. In this example, there are too many dots, but it will be x1, x2 squared, x3 squared. But so the point is that once you can do the surgeries using Frobenius algebra properties of A to determine the evaluation of any such closed form to an integer. And then once you can evaluate these things to integers, this is in Z, this is in Z, you can say what it means to have a linear relation on forms F with given boundary gamma. And this allows you to define the state space. Now, this is known as what people call universal construction of topological theories. When you have numbers for closed and manifolds, and you build state spaces for n-1 manifolds in this way. So here we're just doing it in a slightly different setup. So the idea this allows you to build a state space for any gamma. You can derive kind of, you can replace. You can sort of extend or lift these relations to direct some decompositions, where you would say, for instance, that the state space H of this graph is isomorphic to the direct sum of state spaces of these 2 graphs. So after, yes.
You define the relation of space that is what is the evidence?
Yeah, yes. It's sort of you hide the complexity to be sorted out later. You say that our state space of gamma, of a graph gamma, has a spanning set, symbols of forms F, such that the boundary of F is gamma, modular relations. And to define the relations, again, you define them implicitly. You say that there is a relation, linear combinations of forms with boundary gamma, and its coefficient is 0, if no matter how you glue a form on the top, to get a closed form F prime Fi, you should have a relation on integers. And we can evaluate this form using the Frobenius algebra structure of A and B that we have, because sort of if you have just a facet by itself without seams, that is controlled by a homology of CP2. And when we have a seam, that we can pull everything else away from the seam except for these 3 disks with dots. And that we can evaluate by knowing the trace map, on the homology of FL3.
So remember, if you apply this candidate relation to some form, and taking the trace equals 0 for any F prime.
Yes, for any. Yeah, so it's an implicit definition, but it turns out to work well in this case. In this case, you can check that with this definition, you can check that the Kuiper-Berg-Skene relations, they lift to direct some decompositions for state spaces. So a web which has the subweb, its state space is going to be canonically isomorphic to the direct sum of state spaces for these two webs. Yes, yeah. So potentially, I mean, potentially there are lots of forms. So this definition is, so you need to use this definition to kind of carefully simplify things. But potentially, so if even this was your graph gamma, you know what's going to happen. You have a seam connecting these 2 points, but you might also have a seam somewhere strictly inside, and you might have some genus. You might have dots that are used. So you sort of. So for instance, this could be your form or something more complicated. But this already can be simplified. You can just do surgery here to get rid of this handle at the cost of having some dots and linear combinations. You can do surgery on these 2 handles to split this apart and evaluate it to an integer. So you can, I mean, you can kind of step by step, you can simplify this form with boundary. But so what one proof is that you just use this to show that there are direct sum decompositions. So how do you establish this direct sum decomposition? To establish this direct sum decomposition, so first you derive some scaling relations on forms. You kind of, if a form has some local appearance, form V1, you just show that some linear combinations are equal to 0. So you derive a bunch of scaling relations. For instance, one scaling relation could be that if you take the sum of 3 forms where you put a dot here, or a dot here, or a dot here, some of the 3 terms, that's 0. And that's because in the homology of the flag variety, you have relation that x1 plus x2 plus x3 is 0. So you derive some relations. You also derive to derive this direct sum decomposition, you construct a cobordism between this web gamma and say one of these 2 webs by, let me draw seams in blue. I say let us have these seams. So look at the cobordism from gamma to gamma null, where you sort of you match these 2 points. So it goes from gamma to gamma null. So this gives you a map from H of gamma to H of gamma null. Now, if you reflect this form to the opposite side, you get a map back. So call this map beta 1 alpha, beta null alpha null. And then if you rotate this form by 90 degrees, you get a similar map from H of gamma to H of gamma 1. So just using this form back and forth in both directions and rotating. You can rotate at 90 degrees to get a cobordism into this web and back. So you get 4 maps within these forms, and then you check various relations. You check that alpha null, beta null, this composition is equal to the identity on H of gamma null. And likewise, you check that this is identity. And then you can check that alpha null beta 1 is 0. Alpha null beta 1 is 0. Picture-wise is going to be the following. If you draw the picture, you'll discover that you just create a bubble. You create a bubble sticking out of a facet, sticking out of the plane. And if there are no dots, I mean, there are no dots on this facet, then this is 0. You can check that this is 0. If you were to put a dot, that would be plus or minus identity, but not 0. So you get these relations, and finally get the relation that if you do beta 1 alpha 1 plus beta null gamma null, this is identity on the state space of gamma. And these relations together will tell you that H of gamma is canonically h of gamma null plus h of gamma 1. So you lift the scaling relation, you lift the scaling relations on webs to isomorphism of state spaces. And this is how you can derive that and get the theorem that the graded rank of the state space of gamma is the quantum SL3 invariant of gamma. Okay, so now, and then you can, like using the ideas we discussed, you can replace these relations by long exact sequences and define homology groups for links in this way. Let me see. So I should end at noon, right? It's until noon. Yeah. Okay. So that's the idea. So this is for SL3 webs. I mean, there's been lots of work on SLN webs and forms as well. So one thing I want to point out is that there's lots of interest in SLN webs from the view because of their connections to character varieties, their connection to stated scale modules, their connection to some interesting stories in physics. So I think there's a fair amount of interest in SLN webs from different viewpoints, also from the cluster algebra story. But there's definitely like a belief that much of the story is going to be categorified in a similar way to this codification. So here webs, they give you they have quantum invariance, but you can go one dimension up, get to forms, and get to homology groups for webs and links. And I should just mention that I want to mention that when you look at webs in the context of webs and surfaces, character varieties, stated scale algebras, and what's important is what happens on the boundary of the web. Now, how does, and of course, the webs with boundary, they go back to the original work of Greg Kuperberg, where if you look at all webs with a given boundary is determined by a sequence of signs plus or minus, telling you what the orientation of the web is near the boundary points. So for instance, for the sequence plus minus sequence epsilon. So in the story of webs, this the scaling space of webs with this boundary modular with relations have two basis elements. These are known as examples of Kuperberg non-elliptic webs. That will give you a basis of that of the space for a given sequence of science. These are non-elliptic webs, so they cannot be simplified using any of these relations. So this is a basis of the space I sub epsilon invariance in the corresponding tensor product of these. So now what happens after codification? So after codification, the space becomes the graph in the group of certain category. Let me call the category C sub epsilon. So this is category. This category behaves like the category of projective modules over some finite dimensional algebra, but it's a very special algebra. It's just hard to guess. And the way to guess it is the following. So you look at webs with given boundary. Let me call this web gamma null gamma 1. And so it should become an object of this category. So it should be an object O0, O1 of category C epsilon. And so what should be the homes from, say, gamma null to gamma 1? So the homes from gamma null to gamma 1, they can be guessed as follows. So it should be a vector space and even a graded vector space. So let us take gamma null gamma 1. This is gamma 1. And let us glue them together. So to glue them together, let us reflect one of them. In this case, we reflect gamma null, reverse orientation. So this is gamma null bar, gamma 1 taken together. So we just take the state space of gamma null bar, gamma 1. And this is the homs from gamma 0 to gamma 1 in this category. You can also think of them as describing projective modules over some particular ring, which can be built by taking some of these forms over all gamma 0, gamma 1. And then the morphisms, so if you had gamma 1, gamma 0, and take, say, gamma 0 and put here maybe gamma 2 bar. Let me just schematically draw something here. Then how do you compose hom from gamma? Well, let me just pretend that I changed the order. So hom gamma 0, gamma 2 into hom gamma 1, gamma 2. So each of them becomes the state space of the corresponding web. So this web and this web. And then there's a cobordism similar to the one we already discussed, where you match gamma 0 to its reflection. Just couple it so that you have identity in the middle. And you still have gamma 1 bar here. You still have gamma 1 and gamma 2 bar here. So this gives you composition in this category. And in this way, you can, so you build a category, but you can also describe it as an algebra with a lots of idempotents which single out these objects of the category. Sorry?
What is the gamma 0 bar?
Gamma, yeah, this is a reflection. Yeah, so this is a reflection. Yeah. So we just kind of reduce things to the case of closed webs by coupling them together to get a closed web and take its state space. Also, this ring is described in the work of Daniel Tibinauer. He is here, joined with Pedro Vaz. Which paper was it? Pedro Vaz and yeah. So this, so your paper on SL3 webs. Marco McKay and Paz. McKay and Paz. Yeah. Pan. Yeah, thank you. So the idea is that you can just kind of keep building things by reducing to the closed case, and you get this interesting, you get these rings. Of course, these rings get very complicated as you increase the number of signs. You can define them in this way, reduce them to the closed case, to closed webs, and then, but suddenly you get interesting properties such as if you take center of this ring, particular ring. So in your paper, you show that it's like a homology of certain Spartanstein variety, for nilpotents with 3 blocks. And then you can guess that this should be upgraded to the result that this ring should be related to the, you can see it inside the derived category of modules of the corresponding Nakajima quill variety, because if you take the Spartanstein variety and thicken it to twice the dimension to make it a smooth variety, you get a particular example of a quill variety. And then you can guess that you can recover this category by picking suitable objects, suitable coherent sheaves on the quill variety, and taking their X groups. And so you kind of get a very rich structure which connects to many topics in representation theory and geometry. But so I'm telling you this example because to point out that if you want to kind of establish a better connection to state and scaling algebras to character varieties, so from the categorified level, then you're going to be seeing not just closed webs, but this webs with boundary, and then you'll be getting into this kind of categories, lifting what you see inside the disk, so lifting invariant spaces in tensor products of SL3 or SL representations, lifting them to categorical level. So, but of course, I think it's an open problem, for instance, to categorify stated scaling algebras. But I think that forms definitely give one hint where to look for these verifications. And again, I want to the kind of punchline of my talk was that there is one level of structure above the theory of webs and web invariants, and that's given by these forms and corresponding categories of modules of some extremely special algebras that can be traced throughout representation theory, modular representation theory, quiver Hecke algebras, verified quantum groups, and things like derived categories of shifts on coherent on quiver varieties. But you have link homology, part of the story, and link homomorphisms giving you a very rigid structure on how these categories behave and interact. So in particular, they interact through functors given by tangles and natural transformations between functors given by tangle homomorphisms in particular. So it's a very rigid story, but a very beautiful story, which I think more applications in the future. And I think it's definitely an open question. Categorify things beyond this disk case, categorify the algebra functions on character varieties or status-scan modules. But this tells you what you see inside the disk, but without inside the disk. But in the status-scan algebras, there are some complicated boundary properties of what happens on the boundary, what happens inside the surface, and that's not understood from this viewpoint on the categorified level. Thank you.